Well, a warm welcome to everyone to our new features update webinar for Q2 2022. Thank you very much for joining us today. My name is Paul Lethbridge and I'm the Director of Product Solutions and Marketing here at Simscale. And I'll be your host today. Now, today's presenter is David Heine, the CEO and co-founder of Simscale. David has a background in fluid dynamics and high performance computing. He holds a master's double degree in mathematics and computational sciences and engineering from TU Munich and Georgia Tech in Atlanta. Please feel free to use the chat panel to introduce yourself and also to ask questions using the question option there, the question panel. And what we'll do is we'll answer your questions during the Q&A session right at the very end. A reminder that your microphones will remain on mute during the presentation. And with that, I'll hand over to David.
Thanks a lot, Paul, and also a warm welcome from my side. Excited to have you all here and excited to actually show you what the team has been working on for the past couple of weeks. We're including features here all the way, I think, back to April that we're excited to show you. Before we go through all of the new things you'll find in Simskill, I think it's worthwhile to just, for 30 seconds, quickly remind ourselves, or, for the ones that don't know Simskill, too well yet what Simskill is about. And Simskill's purpose is about empowering every engineer to innovate faster by making simulation truly accessible. And with truly accessible, we mean like technically accessible, economically accessible, and also accessible at any scale. And that, very much sounds like a slogan, but that is like that purpose statement informs a lot of what we do here at Simskill, how we sell, how we market, and also how we build the product. And to that end, like technically accessible means for us that a user, an engineer, a designer that is about to make a design decision shouldn't be limited by hardware, shouldn't be limited by software licensing policies. The simulation methods he or she accesses must be robust, accurate, and fast, right? If they are not accurate, there's no point in making engineering decisions based on them. If they're not fast, you're not going to use them very often. If they're not robust, you're not going to debug simulations for a long time. So these are table stakes to make simulation technically accessible. And then lastly, oftentimes organizations turn to us or work with us when they are looking to deploy simulation earlier and broader in design processes when in their organization. So it's oftentimes means that novice users, new users to simulation, designers, engineers, need to learn simulation and Simskill. So it must be easy to learn and use. And that's what we sort of like, those are the aspects that we believe are, define technical accessibility. Economic accessibility, that's easier, cost-effective and fair, also at large rollouts, dozens, hundreds of engineers. And then at any scale, the obvious, scalability term is computationally scalable. So being able to solve large problems or being able to solve many different design versions at the same time. But a more subtle aspect that we oftentimes help organizations overcome is how do you make simulation organizationally scalable? So when dozens or hundreds of engineers are using simulation, there's certain challenges involved. How do you make sure that simulation best practices are stuck to? How do you make sure that every engineer uses the appropriate material data, etc.? And so the reason why I'm sort of listing all of this is that we're going to go now through 12 or 13 new features in Simscale, and somehow they all go back to those fundamental principles of making simulation more accessible. For example, we're going to talk about, or we're going to show a new solver, a new simulation method that we've built to make thermal simulations faster and more robust. I'm going to show that in a second. We have introduced some new preprocessing features, for example, a surface wrapping method that also goes into the bucket of making simulations more robust, enabling engineers, designers to work with badly prepared CAD data, so in that bucket. But then there's also aspects around organizational scalability. We're going to introduce a new materials data management approach or a new material library where materials data can be shared across the organization, can be uploaded programmatically from third-party systems. And so that goes into, organizational scalability. And so in one way or the other, all of the features and the new things we've built relate to Simskill's purpose about making simulation more accessible. All right, without further ado, I'd suggest we go through the meaty part. And we'll start with a new, like we've developed for the past couple of months actually already, an immersed boundary method on top of our standard finite volume solver, particularly to enable very challenging thermal simulations in a much faster and more robust way. And as they say, show, don't tell. And so for that one, we're gonna take a look at a video. I'm gonna show a few things also live on the platform, but this one is much easier explained on a quick video. So let's take a look here. So what we look at here is a lighting device, an LED assembly. We can see all the small LEDs here in the front that radiate or dissipate their heat, and at the back we can see a heatsink, and the whole thing is passively cooled. And that's a simulation that actually, Simskill can already do for a while, convection, conduction, radiation coupled. But so far, Simskill used a body-fitted mesh generation for it, a body-fitted finite volume method. And that we can see here. So if we scroll in and if we look at the actual mesh that was used, it's body-fitted, and it generates many tiny cells close to the geometry. Now we can see we introduced an immersed boundary method that is actually able to reproduce the same results. However, it uses a fraction of the cells and in turn a fraction of the cell count. So here we can see that the mesh isn't body fitted, but it's immersed and sort of cuts through the boundary. And by that, mesh generation is much faster, much more efficient in terms of cell count. And so here's again the difference. So this is body fitted, and for this assembly, we used 47 million cells in order to resolve the entire geometry and resolve all the fine detail of those fins. And with the immersed boundary method with the new approach, a fraction of the cell count, and as such, you can turn around such a simulation, in minutes, what took hours before. And I think the benefit is obvious here that as an engineer dealing with thermal management, that you're able to, without CAD cleanup, without a lot of, mesh, tweaking, etc., being able to turn around such a complex thermal simulation in minutes gives you an edge in just stepping through more iterations, innovating faster. Good. Now, a second one, so that was electronics cooling, a big focus of ours where we've been investing for a while. Now, other application area, rotating machinery and flow control, something we've also spent now for the past couple of months building more and more of our capabilities out for that. Today, what we want to show is some features around mesh controls as well as result controls. And for that, we'll also take a look at the video. So let's jump back here. So here we can see this is a quadcopter, and we can see it's a transient rotating machinery analysis, and we can see, okay, nicely the thrust is being computed, and we can visualize this nicely. Okay, so far so good. So far we could still do that, but if you now can see what we've now introduced for this solver, the specific subsonic solver that we're using for rotating machinery applications, we do have now the ability to control the mesh locally. So far, a completely automatic mesh generation was used for this specific solver. And now we caught up here and introduced also local mesh sizing, local mesh control for the solver we're using for rotating machinery applications. Easily defined, you can see here in the setup that you define simply via geometry primitives the region that you want to refine, and you give a target cell size. Something that Simscale was already able to do in other analysis types, but for subsonic analysis types, we just recently introduced those. I think also here, the benefits of local mesh controls, I think, are fairly obvious. This is a benchmark a case we computed, and we compared Simskill results with literature as well as other commercial CFD codes, and we see a good trend. And thanks to now local mesh sizing, thanks to another new feature we introduced is that simulation results are now streamed back in real time. Thanks to those, you're now able to compute at the same accuracy, but in a much faster turnaround time because you're able to control your mesh more fine granular. That's for rotating machinery. Paul told me at the beginning of this session, and 30 minutes, we should be there. So I'll try to speed up here a bit because we have a lot of features still to go through. So that was electronics cooling, rotating machinery. We're going to go through the additional application-specific features and enhancements first, and then later on there's a couple of general purpose improvements that we're going to show later. So much for rotating machinery and flow control. Oh, no, that's actually not true. We have another one for rotating machinery and flow control. We introduced new physics, and that is a first cavitation model for the subsonic analysis type, where you're able to simulate local cavitation or the local risk of cavitation inside turbomachinery. Very relevant, again, for engineers dealing with all sorts of hydraulic turbomachinery. Here we're looking at a rocket pump, also water turbines, these kinds of things. And obviously, not just is cavitation model oftentimes important, or at least considering not ignoring cavitation, oftentimes it's important for accuracy, true, that you're getting the right performance predictions, but also the cavitation itself is oftentimes of high interest because obviously one wants to reduce the risk or at least limit the regions where cavitation can occur. Good. From rotating machinery into another area that we focus on, architecture, AEC. And we've introduced two new features here in the last few weeks. One is we do a lot of work in urban wind prediction, external aerodynamics analysis of building facades and pedestrian wind comfort. And now we have the ability to define an atmospheric boundary layer inlet condition based on, you can see it here, only 4 parameters, or even actually 3. So far, you could already in Simskill define such an inlet, but you needed to do the math yourself and then upload effectively a spreadsheet that defined the velocity and the turbulence quantities at the inlet. Now, Simskill does that for you. And you only need to enter a few parameters to define the ABL at the inlet. Another one, also in that direction, we're using a lattice Boltzmann solver for these types of analysis, pacefish, and that is a transient or unsteady solver, and that means that the result output of that solver can be quite sizable. Thanks for Simskill being cloud native, you don't need to deal with this locally, so that's inherently not an issue with respect to storage or handling that. But once you want to visualize it and once you want to do further processing of those results, at times you're interested in limiting the result size that the solver exports. And so you have now more control over this in the analysis types around external analysis, external aerodynamics analysis of buildings, where you can define only region of interest where surface data, volume data, etc., is being exported, and as such, the result data set is much smaller and much easier to handle in downstream further processing of that data. Good. We had electronics, rotating machinery. That was on AEC. Lastly, a quick new boundary condition for structural analysis. Here we introduced, because the structural analysis capabilities in Simskill are oftentimes used in conjunction with electronics cooling, with rotating equipment, etc. And this here is where a lot of our customers in electronics requested the ability to for a base excitation boundary condition. That means Simskill was already capable of doing frequency analysis and modal analysis, harmonic analysis, but now the harmonic analysis is able, with a new boundary condition, that you can define the excitation that is given on a structure based on magnitude as well as speed of that acceleration, and that is put in as a boundary condition, and as a result, you can see at which frequency, typically you stepped in through different frequencies, different stresses occur. And so typically based on a specific excitation, once that excitation hits a natural frequency of a structure, you have the highest stresses. But that's base excitation boundary condition for structural analysis, specifically relevant for engineers, designers dealing with electronics packaging. Good. Now, these were all the application-specific enhancements in electronics, rotating machinery, AEC, and structural analysis. Now, there's a whole host of, we call it general improvements that are relevant independent of which application area or industry you're working in. One that we're very excited about, and that was requested for a long time by our largest customers, is the ability to manage materials data in a better way across projects and across users within an organization. And so on the right, you can see the new layout of the material library that you see when you're adding materials in Simskill. What you're always used to, if you're a Simskill user, what you should be used to is the standard library, where Simskill provides a set of standard materials data that is used on a day-to-day basis in most applications. Now, two new things that I introduced. The first one is a personal library where you are able to import and define your custom set of materials that is then accessible across all of your projects that you're working on in Simskill. So it's effectively a list of your custom materials that you can manage for your personal use, and that is accessible across all of those projects. And so one step further is now for an enterprise or a Teams account of Simskill, also the ability to define a set of materials centrally and share them in a safe way across the entire team, across all users within an organization on Simskill. And that obviously is something that as an organization wants to make sure that appropriate materials data is being used for simulations, that there's control over that, and that best practices are followed. And so such a shared material library sort of is good for consistency and making sure that the users within an organization stick to it, but also in terms of the management side for the organization of that data. There's the ability to upload all of this data programmatically. So our customers typically have some third-party tool or some third-party library where they do manage their materials in. And so Simskill provides now an API access where such material data can simply programmatically be transferred into Simskill and also kept in sync with whatever third-party tool you might be using or an account might be using. So that's on materials data management. Next up, and that's one we're going to actually, before we look into this, that's one we're going to actually look at in live on. So I could quickly click here and load Simskill. And while Simskill loads, that affords me also the ability to quickly point out, like a presentation or a webinar of something like this is nice, but I think there's nothing better than experiencing this yourself. So all of these features are live on Simskill. They're in production. And so you can just, if you do not have an account yet on Simskill, just create an account, takes you 30 seconds, and you can test everything I'm showing you yourself, right, and see how it works for you. And of course, if you already have an account, just sign in and give these new features a spin. You're basically one browser window away from you. Okay, so quickly, let's take a look at the new compare ability that we introduced in the post-processor. Here we can see a little CNC table or CNC machine, and you can see already, if you look closely on the displacement field, we can see the thing is bended here to the right. Let's move this a bit up. You can see how it bends over here to the right. And that is because the megapascal, where are we? 250. That is because the load scenario is that the tip of where the tool is being pushed to the right and to the back. And so we can see how the structure responds. And more important in such a case for a CNC table, more important than the von Mises stress is actually the displacement. And so let's visualize the displacement. And as you're used to, we can inspect now these types of things. So we have 7 millimeters, 0.7 millimeters displacement. Let's make this proper down here. All right, and now the typical scenario is then an iterative design process, simulation-driven design. I would take this and would say, okay, 0.7 millimeters for this, hobby application, that might not be acceptable. So the deformation is too high. So I want to strengthen the structure and make it, that it deforms less. And so I've already done that. I'll not want to show you the entire sort of design process, but more now compare the new design with this baseline design. So I can see that there's the compare functionality at the top. I press it, and I can now see all the runs I have in this project, where I can now compare simulations results side by side. So in this case, I had my baseline scenario that deformed too much. I ran the same simulation with a new reinforced model, and I can now see those two simulations results side by side and compare them. And what we can, of course, immediately see is that here you can see this massive structure here on the right, that I have a much stronger back, and it deforms much less, somewhere in the, I don't know, less than 1/10 of a millimeter. So what to be expected. I can also unsync the views, compare them, and then I can also step through different fields. I think you get the idea. Manipulate those and compare them nicely. Something that again is in support of going back to easy to use and then fast, that you're able to quickly step through different designs, that you're able to quickly compare different designs, go back to your authoring system, to your CAD systems, and make the design changes based on the information you got from the simulation. Available now to everyone on the platforms. I encourage you to give it a spin yourself. So that's the side-by-side post-processing that we introduced. Good. The also a new post-processing feature is that now you can export GIF animations and videos directly from Simscale's post-processor. So far, you always were needed an external screen capture tool or something in that direction to make it work. Now that capability is introduced directly within Simskill. Let's continue. I think we're good on time. We might just make it. Let's see. All right. Next up is a preprocessing technology that we introduced specifically for external aerodynamics applications. And there's many. At Simskill, we know from working with thousands of engineering organizations, hundreds of thousands of users, that in a real world, in a day-to-day engineering workflow, you just have to deal with geometry that isn't well prepared for simulation. And the moment you're asking an engineer or a designer to prepare something well for simulation, it already sets the hurdle high for that person to actually use simulation. And so to make simulation truly accessible, it goes without saying that we're investing a lot in dealing with all sorts of CAD models and dealing gracefully with all sorts of CAD models. And so we have a whole host of methods by now. The immersed boundary method we've seen earlier is one of those methods that allow to deal with complex geometry, with excessive detail, with geometry that's dirty or ill-defined. And surface wrapping is another one. Let's see it in action. So we hop over to a video again. And what we can see here is a vehicle model, a car model, and we can see it's a ton of surface. It's a lot of sheets that we're looking at. We can see in the right slit facet bodies. We have self-intersecting facets. So it's a typical sort of very nasty surface model. Very hard to clean up. What's now possible is what you can see here is that we have a wrap surface operation where you assign simply the surfaces you want to wrap. And then automatically, this takes about 30 seconds, 40 seconds, automatically a wrapped surface is generated around that structure and around all the faces you had. And specifically for external aerodynamics analysis, that's sometimes that's all you need. You don't need the entire interior. Right? Same story with other vehicles, or in this case also comes in handy for architecture applications where you also oftentimes deal with excessive detail. Good. So that's that. We can see it again here on the right, the two models before and after wrapping. Before 650, here we have the exact number of sheets we had, intersecting, yada, yada, yada. And to really make this a clean B-rep solid, almost impossible. And so a surface wrap creates a 100% watertight solid that can then actually be used on Simskill for further downstream operations. So this is a clean geometry that then can participate in Boolean operations where you extract the wind tunnel around it and these sorts of things. Ready for simulation, as we've seen earlier. Good. That is on pre-processing. Next up, we have a few improvements on the general design process workflow, the general design workflow, because simulation is one thing, but holistically, simulation just serves the purpose of making informed design decisions. And so as such, we've been investing more in from the CAD system where you author your geometry and then sort of the workflow of getting the simulation results and going back and iterating faster. And so what we're introducing today is a fully associative import from on-chip CAD models into Simskill that ultimately enables simulation-driven design. And also here, let's take a look at a quick screen capture to see how that works. Good. What we look at here is a cover of an inverter design, and we can see it's fixed on a bunch of holes around, and then there's a force applied on top of it. And now I can see sort of how this inverter cover bends down and how it deforms about 1 millimeter in that part. And for this specific scenario, let's say 1 millimeter deformation is too much, stresses are too high. So I go back to my CAD model in Onshape, and here I can see because this is nice, here I can see how from my main version to the V1 version, I introduced a few more ribs here at the bottom of at the back part of the inverter cover. I do that in Onshape, and then in Simskill, I simply import the new geometry. You can see it here in the top left. I import the new geometry via the automatic import from Onshape. I import it as a new version, in this case V1. And now comes the important part. So I imported it, and when I now run the exact same simulation with the new geometry, all simulation assignments are retained. So you can see it here. I click on the geometry, I change the reference to the version 1 that I just built with the ribs in the rear part, and I don't need to do anything. It asks me if I want to keep the contacts or not, relevant for some more complex assembly analyses. In this case, I'll exchange them and run the new run without any boundary condition assignment, nothing, right? So within 10 seconds, I have the new simulation up and running. And again, we can see it here as we would expect. On the right, the ripped or the version with the more rips, on the left, no rips. Again, as we would expect, lower deformation. Good. Now, as the quick summary, something like the associative import, like an on-chip import was available on Simskill for a long time, but it wasn't fully associative when new versions came in. Now, simulation assignments inside Simskill are retained across different versions of imports of Onshape, and by that allows me a much faster cycle from design to simulation to design, and yeah, ultimately enabling a simulation-driven design process. Good. So that's exciting news for Onshape users. And then for SolidWorks users, we have exciting news as well, where we did develop a Simscale plugin inside SolidWorks, also with the ultimate goal to facilitate a faster simulation-driven design process from SolidWorks to Simscale. Let's take a look at how that looks. Here I'm inside SolidWorks. I'm working on structure, sort of this sort of spreader beam. And here we can see it on the left. This is the Simscale plugin. So we have a little Simscale plugin, which effectively just allows you to manage the data transfer between SolidWorks and Simscale, where you can see I'm assigning a project where I want to upload this CAD model into. I don't have to export anything anymore. I don't need to manage data in some folder. That is automatically taken care of within the SolidWorks plugin. It exports up to Simskill. It does some bookkeeping inside SolidWorks to guarantee associative updates. We're going to see that in a second. I run my simulation in Simskill, go back, see I might have over-engineered, over-dimensioned this one. So I'm taking away a bit of material. We can see here the feature differences in those beams. Again, same story. Go back to the Simskill plugin, upload the new model, and now again the associativity here is important. I change the geometry inside Simskill. Nothing needs to be reassigned. My boundary condition assignments, all assignments I have in place are kept in place. I can run again within 10 seconds. I'm underway with my new version, and I go back to being able to directly compare side-by-side comparisons and iterate further in my simulation-driven design process. All right, also here, the quick summary. Oh, one too far. Also here, the quick summary. That we here introduced the plugin for two reasons. To make the data transfer more convenient, that you don't need to save anything, export anything from SolidWorks. All of this is taken care of by the plugin. And then B, that the associativity of different versions that you upload to Simskill is maintained. And by that, you don't need to do any additional new assignment when you're working with SolidWorks and Simskill side by side. We can see here, this has already been in early testing with many of our customers. And if you're currently a SolidWorks user, I encourage you, reach out. Reach out to us. We're currently having this in beta mode. We'll encourage you to use it, and we're rolling it out further as it matures. Good. Almost there. I think this is the last one we wanted to show, and we're also going to end this one with a live demo. So let's take a look at this field calculator. And the field calculator is also a new post-processing feature that allows you to compute or calculate derivative result fields from the simulation results you produced directly within Simskill. What that means, we're going to see here. Let's refresh this real quick. That we have a nice new view. And what we're looking at here is a shaft of an electric motor. And that shaft is on torque. So we have the torque load over here and we have it fixed over there. And we're looking at the von Mises stress. And obviously the stresses are the highest in front there at the shaft, right? Okay, that's what we would expect. Now, what we would be interested in such a scenario is the factor of safety. This is steel, yield stress of 250 megapascal, and we want to make sure that our factor of safety is north of 2. Right? We have 10 Newton meter torque load here. And so what we now can do to conveniently directly visualize the factor of safety is with the new feed calculator feature. So we're adding this, and you can see you can now basically define a new field. In our case, it's factor of safety. That has a very simple calculation, 250 megapascal divided by, so the yield stress divided by the actual stress. And this is now computed, and we see the new field showing up as a result quantity that I can now visualize. And so let's visualize this one. I don't see a lot yet. And because it's a factor of safety, what we want to do is we actually want to visualize this in an inverted way. Let's bring this a bit down. Let's say 200. Now I'm talking. So obviously we can see down here in the big shaft where the torque load is applied, high factor of safety, there's little stresses. Here in the front, we see it gets more interesting. But the minimum factor of safety we have in front of the shaft is still north of 3, right? So we could generally say check mark. This is not about motor design or shaft design. This is really just about the ability to now directly within Simskill's post-processor compute result quantities that are derivatives of existing simulation results that you've been computing. Again, avoids the necessity to go to a spreadsheet, avoids the necessity to go to a third-party tool to further process these results. Good. Paul, I think that was it. For everyone in the audience, thank you very much. Like, my last words here would really be that, I think it's really important that all of this is accessible to you right away. So I'd encourage you, if one of these piqued your interest, try them yourself. Don't take my word for it. Give it a spin yourself on Simskill. Just open up a browser and fire these things up. Thanks a lot.
David, thank you very much. Excellent. So we are a little bit over time, but we've had a few questions come in. If you're game, David, I'll select a couple of them, and
of course.
Brilliant. So I'll just look down the list. A couple of them came in on chat, a couple of them came in on the question option. So let me think. What type of elements does the IBM method use?
What type of what?
Elements. Cells.
Oh, Cartesian. Yeah, completely Cartesian. Yeah.
Excellent. Okay. That's a question, interesting one came up. obviously this is all functioning in the browser, which is brilliant. What browsers are supported?
I think the short answer is everything that can run WebGL, which to the best of my knowledge, all modern browsers do. So there might be very old versions, that have been certified by an organization where we here and there had issues because they couldn't update to a more modern browser. But every modern browser can run it. So we have customers actually that are using all browsers.
Brilliant. All right, David. I think we're in the interest of time. Let's move on to the last slide.
Oh, yeah, that's my job, right?
Yes, that's okay. Thank you. So once again, David, thanks very much for running through that and especially showing the live demos. It's excellent. So I trust everyone found this really interesting. I had posted a link into the chat so you can understand so you can actually sign up and start simulating now. So I hope you're now very keen to have a go and try out some of these new features that David has explained. They're all available now as well, which was one of the other questions. Also, you can request a one-on-one demo, so you can contact us directly at sales@simscale.com, and you'll get a response from an application engineer within 24 hours. Also, if you want to listen to this again, or you've got a colleague who couldn't make today's webinar, there will be a link to the recorded version of this webinar made available to all those that registered, all participants afterwards. So with that, thank you very much, everyone, for attending. This brings us to the end of today's webinar. Thank you.
Thanks a lot. Bye-bye.